Hi everyone, now it's topic 3, statistical process control using X-bar chart. So in the previous topics, what we have learned in topic 1, we defined total quality management, and also we briefly overview about normal distribution and the standard normal distribution. And then in topic 2, we learned how to use a normal distribution to calculate the yield rate, and also we know how to use CP index to measure how good the process is. And here in topic 3, we will take a little bit different approach. In the previous topic, actually, we look at each product and whether this product's output is within design specification or not. And by doing this, we can decide each product, whether each product is defective or non-defective. And the yield rate itself is the probability of selecting these non-defective products. But from this topic, in topic 3, what we will looking at is not each product, but the process that we use to make products or services. So, to understand this statistical process control, first we have to distinguish two different reasons of process variability. First one is called common causes of variation, and the other one is called special causes of variation. Even in the previous topic, we mentioned the machine cannot be perfect, and if you draw the distribution of product output, it may follow normal distribution. That means the product output can have some variations. For example, the depth of a desk, the average is 2 centimeters, but it could be 2.1, it could be 1.9 centimeters. However, if we predict this variation, we call this common causes of variation. Also, because of common causes of variation, a process has a non-zero standard deviation, sigma. In contrast, the special causes of variation in a process is variation due to non-routine factors. So this variation we did not expect, but this represents deviations from standard operating procedures, or in other words, this means a standard deviation that you get is far greater, or sometimes it could be far smaller than the normal value of sigma. So to better understand the difference between common causes of variation and the special causes of variations, we can consider these scenarios. Like here, let's say there is a timeline, and in this timeline, we want to measure the process multiple times. So like here T1, and here T2, and here let's say T3. For example, the first month, the second month, and the third month, and also fourth month, we monitor the process and we get some samples. And let's say in the first month, when you draw some sample products, and when you describe the distribution of this product output, so let's say you got these normal distributions. And in this normal distribution, yes, we have a non-zero standard deviation. That is the reason why we have this bell-shaped curve. So here we know that sigma value that is not equals to 0. Therefore, we have this bell-shaped curve. If the process is perfect, we may not have this bell-shaped curve, but a peak, vertical line instead of this bell-shaped curve. In this case, variance may be just 0. So therefore, when we have this kind of distribution, as we learned in the previous topic, we expect these non-zero standard deviations, and we expect this bell-shaped normal distribution curve. In this case, this non-zero variation is called common causes of variations. Now, in the second month, let's suppose that we got similar distribution curve like this. Then, we know that this first standard deviation is very similar to this second, standard deviations like in time 2, then this is pretty similar. Therefore, we still expect this variation even in the second month. Now, in third month, let's assume that when we got the distribution of this product output, we got like this very spreaded kind of distribution. In this case, let's say this standard deviation, process standard deviation of 3 is far, far greater than the previous standard deviation. Then it's what we did not expect. But in fourth month, let's see when we draw the distribution. Now it goes back to kind of a normal distribution curve that we expected. Then it's again still we have some variation, and that's what is expected. It's called the common causes of variation. But here, this case, that is very different from other standard deviation. Then we call this what? Special causes of variation. So in this process control, what we are interested in the previous topic, actually we are interested in given this kind of distribution, what is the yield rate and the CP index. But from now on, by monitoring the process, what we want to detect is whether there is some significant variations from the normal condition in terms of process. Or, in other words, we want to detect this kind of special causes of variation, and that is main objective of using statistical process control. So now we understand the main objective of process control is detecting any special causes of variation. So, process control refers to monitoring quality while the product or service is being produced. So that is very different from product design in the previous topic. So by detecting this any shift in the process that signals that future products may not meet specifications, we can keep high quality products. So what we are going to do, how we can control this process is we will test the random samples of output from a process, and we will develop a process control chart that will be used to detect the probable presence of special causes of variations. So the method that we are going to use, particularly the process control chart, may look like this. Very soon, we will learn every single detail how to develop this process control chart. But you can get some ideas by looking at this sample process control chart. So what we are going to do is we will collect many different samples. And for each sampling, we will draw a point for each sampling. And then we will check whether this sampling point is inside a certain range or outside this range. So to get this limits, we have to define lower control limit, or here it's called LCL, and we have to also define upper control limit here. So given this control limits, for each sample, we will draw one point, and if this point is within this control limit, we can say process is normal condition or process is in control. And if it's outside this control limit, like from here, then we can say this process is out of control. Again, keep in mind that we are monitoring the product. Now we are monitoring the process. And what we want to see, whether process is in control or out of control. And what we are going to use, we will use a process control chart. So now let's see some details how to develop this process control chart. The step that we are going to follow is actually what you have learned in the statistics class, particularly the hypothesis testing method. Here what we are interested in is whether process is predictable or in control. So the meaning of a process in control is a process that is statistically predictable. This means when this operation or process is running under the normal conditions. However, you have to note that when a process is in control, still there could be common causes of variation, and it's normal to have these common causes of variation. However, there is no special causes of variation, then we call this process as in control. But if there are some special causes of variation, or there is some unexpected conditions in this process, we call this process is out of control. We need to set up a null hypothesis, and this null hypothesis is process is in control. Then, obviously, the alternative hypothesis will be process is out of control or not in control. When we test the hypothesis, but you may remember alpha error. So by adjusting this alpha error, the control limits or critical values will be different. And by definition, the alpha error is the probability that we reject null hypothesis when it is actually true. That is also called type 1 error or false alarm. So in this context, what this alpha error means, suppose you get some samples in the process, and then you test the hypothesis. The hypothesis that we are testing is whether process is in control. So when you test it, now you get some evidence that this process is not in control or process is out of control. So you will reject this null hypothesis and you will make a decision that process is out of control. However, your decision could be false. Your decision could be wrong. So actually, the process is in control, but you make a decision that process is out of control. The probability of this situation where you make a wrong decision that process is out of control when the process is actually in control, this is called alpha error. So you can set up alpha error as like a 5%, or you can change it to 10% or whatever. So by changing this alpha error, keep in mind that the critical values could be different. So we will set the control limits, and this control limit is actually exactly the same concept that is used in statistics textbook, and in the statistics textbook usually it's called critical values. So in operations management domain, although we use different terms such as control limits, but the concept itself you have learned in the statistics course. They are called critical values. So let's see further how to use this hypothesis testing to control the process. So graphically, how we can use this is in the upper graph, you can see that given alpha error, particularly if it's a two-tailed test, you can set alpha over 2 error here on the right side, alpha over 2 on the left side, and by using this, you can set up two boundaries, and in the statistics, they are called two critical values. So by setting up these critical values depending on the alpha error, now you can test the hypothesis by doing some sampling and then drawing this. If this the test statistics is inside these two critical values or in this boundary, we will not reject it or we will accept the null hypothesis, but outside these critical values we will reject the null hypothesis. That's what you have learned in the statistics. So in this process control, how it can be utilized, just draw same distribution like this, but now you draw it kind of vertically. So rotate it in 90 degrees, then you can draw this curve, and similarly based on the alpha error, you can set up two critical values. But now change the terms. Instead of critical values, we use the term control limits. So you can set upper control limit here and the lower control limit here. Now we decided these two control limits, then what you can do, there could be multiple samplings, and each sampling you can draw test statistic value here, and then you can decide if inside this control limit you have to accept the hypothesis, or you can say process is in control. But for example here, the last point, if it's outside these control limits, you can say process is out of control, or you can say that there could be special causes of variation that you did not expect. Now the next question is, then for each sample, yes, I mentioned that we need to get some samples. Then with the samples, which number you have to use to test the hypothesis? In general, in many cases, people use the average of each sample. But it does not have to be average. It could be range, or it could be the proportion of defects, or it could be also number of defects as well. So for each case, there is some different numbers you can use to test the hypothesis, and that is called test statistics. To test the hypothesis, different test statistics can be used, and when you use these different test statistics, you can draw different process control charts as well. So for example, if you use sample average, this control chart is called X-bar control chart. If you use the range of each sample, it's called R chart. And if you use proportion of defects for each sample, it's called P chart. And if you use number of defects, actually it's called C chart. We may not have time to discuss C chart, but we will study the all three charts that include X bar, R, and P charts. So in general, how can we set the control limits? The two limits in your control chart. Upper control limit is usually the center value is average of test statistics, and plus z value multiplied by standard deviation of test statistics. Lower control limit is average of test statistics is center line, and minus z value multiplied by standard deviation of test statistics. I will show you how to get the z value, and I will explain the standard deviation of test statistics for each control chart. But at this point, just to keep in mind that kind of in a general form of control limits looks like this. So also note that the value of z depends on the alpha error. I mentioned before that alpha error, it could be different, and as a kind of tester, you have to set up this alpha error. And if you change the alpha error, the z value will change. When z is given, instead of specified alpha error, we use the term z sigma control limits. Later, I will explain further about this. But for example, if I say, you need to develop 3 sigma control limits, that means z value is 3. If I ask you to develop 2 sigma control chart, now this z value is 2. So now you may wonder how to decide this z value in the control limits. So you may remember now here, if there is a distribution, and if you test the hypothesis, there is alpha error given, right? So what is alpha error? Alpha error is the probability when you make a wrong decision, actually when it is true. So here, here we have two control limits, right? So on the right side it's called upper control limit and the lower control limit. And then how to decide this control limit? The area here on the right side of upper control limit and the area on the left side of this lower control limit, the sum should be this alpha error if it's a two-tailed test. Therefore, here on the right side, this area should be alpha? No, alpha over 2. Since on the left side, we have one more area that should be alpha over 2. So the sum is here, alpha error. So what is the z-value in this control limit, general form of the control limit? Z-value is here at this point. This is called z-value. Okay, so in general, let's see how to find this z-value using standard normal distribution tables. For example, in this case, we want to find the z-value when alpha error equals to 5%. Then, so how to find the z-value in this example here? If there is a distribution, we can set up upper control limit here, upper control limit, and then the point we are looking for is here, and it's called the z-value. So to find this point, this z-value, we have to decide the area. So the area on the right side here, that should be alpha? No, it's a two-tailed test, therefore it's alpha over 2. So in this example, alpha is given as 5%, therefore it's 2.5%. So if it's 2.5%, then the area on the left side here should be, yes, 100% minus 2.5, therefore this is 97.5%. So you have to, look at this 97.5% where? In the standard normal distribution table. Here in this slide, now the area we are looking for is, we know that it's 0.975. Therefore, now, given this value, the area 0.975, we need to decide the z-value. So how can we read the z-value? Here, on the first column, it's 1.9. So until the first decimal point, we can decide it's 1.9. And what is the second decimal point? It's 6. Therefore, the z-value we are looking for is z equals to 1.96. That is how to find the z-value given alpha error. So now we get some big pictures like a general form of control limits and process control chart. So it's time to look at each control chart like X bar chart and R chart and P chart more specifically.